Good. Okay, so I shall introduce myself as the next speaker. So this is joint work with Amy Wilson and Stan Zachary. Is Stan here? Yes, Stan is here.
Hi.
I was getting a little bit worried that that if people ask tricky questions, I would actually have to answer them and not be able to try and hand them over. But so on this Stan did most of the intellectual heavy lifting on the mathematical side, and Amy has put the various examples together. And one thing one could think of this of is a sort of expanded version of my comments on Ben's talk, where this presentation is largely what lies behind that question over whether one can run if you like, a normal auction with a simple additive commodity. And so we give special thanks to National Grid, because it was largely the work we've done with them on the electricity capacity assessment study and capacity market which inspired this, and it's work has been variously supported by them and by different UK Research Council grants. So start off thinking a little bit about what is capacity adequacy assessment. So well, it is important for many reasons. This slide is actually taken from the date of the publication of the first Great Britain electricity capacity assessment study, and I can tell you exactly what I was doing at 6 o'clock on 5th of October 2012, because I got home, put the BBC 6 o'clock news on back in the days when I actually did get home in time to put the BBC 6 o'clock news on, and discovered that this project I'd been involved in was the lead headline. And I started thinking it's a bit like the Wizard of Oz. Toto, I don't think we're in Kansas anymore. This was no longer the normal business of academic research. So then we found the next year again there were also headlines, and then the year after that the results of the study led by Ofgem, the regulator, were much more benign, and there was absolutely no media interest whatsoever. But one point about this is that electricity security of supply is quite a major political media issue. And in terms of utility functions, in one sense, the sort of binary utility function felt by political decision makers, that they either have an electricity security of supply crisis and lose job and career, or they don't. And that's one thing that hangs over decision making in this area. In terms of the what we mean a little bit more specifically, I think about definition of relevant risk indices. So we're interested in the evolution of margin of available supply over demand through peak season. So in the simple version, you might have at different times available convention on the if you like, on the plus side, you've got available conventional and variable generation need to take off demand. Ahead of time, you have to think of all of these as random variables. There's already been some discussion of inclusion of interconnection and storage, and you can define various standard adequacy risk indices. Probably most people are familiar with these. Typically, at least in present day, most practical studies report expected value indices. So this would either be the expected, in the mathematical sense, total duration of shortfall over all the possible realizations of the future peak season that you're studying, or would be energy-based index. There are interesting questions as to whether, as we go forward and bring in much greater variability of supply, these expected value indices give a sufficient picture of the risk profile. Because of course variability about the expected value outcome matters. in decision making. But in terms of defining what we mean by adequacy, it can be a slightly notorious thing trying to define this verbally. So I usually say the quick way of getting an understanding of what we mean by adequacy is to start from the other end and say this is what people refer to as an adequacy risk model, and adequacy problems in the world are things for which this model can say something about. So I'll take that'll do us for this talk. I'll just firstly mention a few things that combinations of Stan and Amy and I have done, which I'm not going to talk about today. One is various analytical results for special cases, where if you choose special cases like this, a small addition of additional generation such as wind or solar, or you're able to make an assumption of exponential function shape of the probability distribution of backgrounds which you're adding the wind or whatever, then you can derive various useful analytical results that give you insights into what's driving the results of calculations. I think this was a paper in the 2014 probabilistic methods applied to power systems. Back then I was known as Chris Dent from Durham. Another piece of work. This is Amy spent much of the last 2 years working on this. Is use of extreme value statistical methods for modelling the process of net demand. Initially, there was some work with National Grid looking at this in a time collapse model, and then we had a project looking at this in time series models. And just one general thing I would flag is that there is not in my view there is not enough statistical work in this area. There certainly seems to be very, very little serious statistical work on modelling the inputs to these calculations, and we seem to have done a macroscopic proportion of it, which says kind of good things about us, but it seems to be quite an omission that there aren't a lot more people doing this. And generally, there seems to be very few statisticians who are working on power system planning questions. And again, this is something of an omission when we're often looking at managing uncertainty. So I would encourage anyone to help draw people in. Finally, I'll just flag a further piece of work that Stan did arising from discussions in Great Britain, where he was looking at the behaviour of the least worst regret decision criterion that's used for decision support in how much capacity to procure, and what aspects of the planning background scenarios considered by the government actually drive the results of this analysis. And there's a paper. I think it's a paper on the archive.
I think so.
Yeah. Yes. The paper on the archive. There's also a presentation. There's also on the International Centre for Mathematical Sciences website. There's a presentation on this that Stan gave a couple of years ago. Okay, so getting on to what I actually am going to talk about, looking at how one brings storage, or indeed, just as an aside, we often refer to this as the paper that underlies this as the storage paper when we're discussing. But in a sense, the real point is it's about how you bring any technology into capacity markets on a common basis. And it's important to think if we are considering storage, what's different about it, and it's also necessary to think what it is different from. So if you look at the other things you get in these calculations, so you might have you have conventional generation. This is Drax, the biggest coal. Well, it was coal plant. They're now converting to biomass largely. It's Whiteley Wind Farm, the largest onshore wind farm in Britain, just near Glasgow. And if we think about traditional demand, not this newfangled demand, which is flexible, but traditional inflexible demand. So storage is different from all of the above in that there is a relevant control action, which is when to use the finite energy you have in the store, and it's different from conventional generation, but not wind generation, in that what you can get from it is not just about mechanical availability. And a lot of the existing ways capacity markets are set up, they originates from when we were only thinking of conventional generation or things that look exactly like it as the resources that we were procuring. A couple of points as to why this difference matters. So if we look at the choice of risk indices, so suppose our index is based on the duration of shortfall in the future season we're studying. That implies that your target is to minimise the duration of shortfall. And so if we have a little cartoon of a shortfall, and you imagine if storage is trying to minimise the duration of shortfall, it might do something like these red triangles. On the other hand, it could minimise shortfall depth by doing the green shape. And in some circumstances, you might think that reducing the maximum depth of shortfall is rather helpful. But of course, this would actually not do anything at all to reduce your, if you like, damage as measured by duration of shortfall. On the other hand, you could also imagine a conventional generating unit which can not only do the red triangles but also do the blue rectangle. And this clearly is making a greater contribution to reducing lost load, but it actually doesn't get any additional credit versus the storage if you're measuring your problems by the duration of time for which there is a shortfall. And the conclusion from this is that these duration, these indices in terms of the total duration of shortfall don't give a fair comparison between different technologies. There doesn't seem to be a way around the fact that you have these issues like in this little cartoon, conventional generation gets no more credit, despite the fact it can clearly do a lot more. So the conclusion is that in order to give fair comparison between storage and other technologies, you need to use energy-based risk indices. And indeed, National Grid and the government did switch to using an energy-based index for coming up with value of storage within the capacity market. A second point where the difference matters is in terms of whether one can work with a simple additive commodity in the capacity market. So if you imagine adding one extra conventional generating unit to the approximately 200-250 that we have in the in Great Britain, then to a very good approximation, if you do your standard risk calculation, then this simply shifts the probability distribution around, shifts its mean, and the slight change in the shape or width is a lower order effect. And as a consequence, you can quite reasonably, because you're only adding or taking away a few units on the margin in a capacity market, you can work with the mean available conventional capacity as a standard simple additive commodity. With wind and storage, it's not so simple. I mean, with wind, you have statistical dependence between units, so you end up having to think of the wind generation as one big block. With storage, you have an energy limit, and it's not straightforward to run an auction without such an additive commodity. And possible resolution of this is the main topic of this talk. So, if we move on to the new material, so I've actually realised that I've got I managed to end up with 2 copies of this slide, but
It's really a good one, so
yeah. It's quite beneficial because there's a little bit more on the second one. So I'll start with the first version because these equations are bigger on the first version. But again, this is just restating the definitions of the risk indices that we've had previously, and the assumptions we're going to require are the first one is sounds a little technical, but it's actually very important. So we're assuming that for running our capacity market, we have some background demand process given against which we're planning, and this effectively means that we have a specific scenario against which we're doing the risk calculations on which our capacity procurement process is based. And this is actually a reasonable. This is a substantial technical complication when you're running a capacity market, because of course 4 years ahead or however long ahead you have uncertainty over what the planning background looks like. But this is the key assumption, that we have some particular scenario chosen. I'm just going to say, rho of R is our risk index if we have a set R of resources procured. There are a couple of, there are 2 technical assumptions on continuity and smoothness, which allow us to develop this marginal theory. And following all of this, we can, if I go to version 2 of the slide, which has an extra little bit on the bottom, we can define a sort of a derivative with respect to firm capacity. So if we add in a small amount of additional capacity, we can simply we can define derivative in this way, and also this allows us to define a kind of first order Taylor expansion. If we add in a small additional resource, a small additional generating unit, then we can define the equivalent firm capacity of the additional resource as based on this definition we've had of the derivative. And some consequences of these definitions. You have an alternative way you can rather than solving this directly in some sort of iterative way to get the equivalent firm capacity. If you have a small resource, you can invert the formula, and this is sort of it's sort of a numerical differentiation of capacity. And you can show fairly easily that as long as you only have generation as resources and you don't have storage, and as long as the derivative with respect to additional small firm capacity of the expected energy unserved is simply minus the loss of load expectation. The sort of intuition behind that is simply that suppose you have that's your demand curve. You have some shortfall. That's your available generating capacity. You have some energy shortfall here, and if you shift the available capacity up and down, then the area that is the area of shortfall that's either added or subtracted is simply the duration times the amount by which you're shifting the available capacity. When there is storage, I mean, making some reasonable assumptions. I mean, one key one which simplifies things very greatly is if we assume that any storage we have is recharged overnight each day. So this is kind of a reasonable assumption if you don't have too much storage on the system, and also one remembers that these calculations are not about actually what will happen day in, day out if there isn't any problem. It's what can happen in extremis if we are in a system stress situation. Involving, I won't talk about the optimal strategy for coordinating multiple stores, but if you see work by Stan Zachary and James Cruz, and also Simon Tinderman's talk in the first workshop, they talk about the optimal strategy in this kind of model. You can derive an equivalent result, which again is quite intuitive as a generalization of what we have here, that the expected energy, the derivative of the expected energy unserved with respect to small increments of firm capacity, it's a similar expression, except you have the loss of load expectation is taken with respect to the total set of resources minus the stores which are empty at the end of the day, and therefore can't contribute anymore. And this gives a nice little observation that based on this, that firm capacity contributes more when you're adding to a portfolio which includes storage resources. Okay, finally, let's talk a little bit about consequences for capacity markets. So we might have two versions of how we think about a capacity market. The first would be to minimise the procurement costs subject to some risk index, and the idea here might be that in some sense we rank the units in order of value for money. So we basically add in the best value for money units first, and just keep going until you hit the risk target, or you achieve the risk target, and you have this this kind of market equilibrium condition satisfied by the sets of units that are the sets of possible units that are getting capacity payments and those that are not. So if you knew the marginal equivalent firm capacities of all of these units ex ante, then you'll be able to rank them according to this. This would be your measure of value for money, and just simply add them in this merit order. Unfortunately, they are not known ex ante, because you don't know what the background is to which you are adding them. So a possible scheme is to start off with initial estimates, i.e. basically have some sort of initial guess at the auction result, calculate marginal EFCs with respect to that, use that to create a merit order, kind of run your auction, and then you get a different set of capacities in merit, and then you recalculate the EFCs, keep going until you hopefully get convergence. The alternative view of how you might look at procurement in a capacity market is an economic approach, where you seek to minimise the cost of procurement plus value of lost load times expected energy unserved. And if all of your resource were firm capacity, you can differentiate, and you end up, if you define cost of new entry as the derivative of cost with respect to resource, you end up with the result loss of load expectation as a function that you end up with the you get back to a risk target in terms of loss of load expectation. So this economic criterion would be equivalent to loss of load would be equivalent to a loss of load expectation equal to the cost of new entry divided by value of lost load. And this result, I'm not sure quite how well known it is. It was certainly used in derivation of the security of supply standard in Great Britain, and is there in its glory in an appendix of a volume of the background materials to the electricity market reform process. I've also seen it pop up in. There's a recent paper by Litvinov and Co. from ISO New England, but I haven't seen it in too many places. But that might just be because I don't look in the right places. If you have variable generation or storage, under this condition for when this would still hold is stated in more detail in the underlying paper, which hopefully soon will be available publicly. Approximately this holds as long as you don't have any sort of strong diurnal variation or statistical association with demand that means that that you end up with if you like, different times of day driving the risk calculation when you add in the variable generation. It doesn't hold for storage. In this case, you would have to work directly either with a risk constraint or work directly with no, this is perfectly timed because I am just coming to there's an example of such an iterative calculation with a representative Great Britain system, and after about a dozen iterations, this did converge. I'd say it did converge. It gets as far as oscillating between two very similar solutions, which is probably in technical mathematical sense that would not be called convergence. And so I better not call it convergence if I'm in this if I'm in this particular institute. But this is what we found. Finally, just to conclude, this proposal on how one might run a capacity market, it was motivated by inclusion of storage, but the real business is allowing any technology to be included on a common basis. Again, following on from discussion after Ben's talk, currently I'm not aware of any scheme which both for including variable generation storage in auctions in a way which both properly reflects the system risk profile and maintains a simple additive commodity. And it's obviously there's a strong preference by people who run auctions to maintain a simple additive commodity, but if maintaining that takes you too far away from properly reflecting the risk profile, then one might think of that as asking for trouble. As I say, we've got paper in full draft, and we have this fairly imminently will be a preprint and submitted somewhere. But we've been saying that for a little while. Anyway, on that note, I shall finish and hand over to my nemesis.
Thanks, Chris. And I should say how enormously important this work is, because I sat on the panel of technical experts who were charged to challenge National Grid on the numbers they came up with, which were informed by the analysis, especially that Stan, Amy and Chris did. And just to put this in perspective, the first auction, the calculation that Chris showed suggested a cost of new entry of £50, 50 gigawatts of stuff out there to be procured. The market came in at £20, but the curve that showed how much more you would have to pay to get a little bit more capacity was extremely cheap. So the difference between those two prices is £1.5 billion a year, continuing for a long time. So the kinds of graphs that Amy produced of how long, how deep, how often, were the kinds of questions we were saying to National Grid, well, what's the answer? And they said they don't know. So the value of doing this research is huge. So that's one first comment. I mean, the interesting thing is, as Chris said, although we have a loss of load expectation of 3 hours a year as our standard, what those graphs that showed the costs versus of having a shortage versus the costs of procuring capacity to reduce those shortages to is actually all on energy unserved. So we actually do it, I think that you would say the National Grid does it probably the right way.
Yeah, well, it's certainly notable that in practice we end up using both at different points in the process. We end up using both the economic and the loss of load expectation version.
Our main criticism was that National Grid didn't really say what the cost of what they called a loss of load was, because they didn't tell us all the things that they could do to minimise that cost. But that's a separate matter. What I would say, and it's very important in the case of storage, what the single electricity market does is publish a matrix saying, if this is how many batteries we have, then this is how we're going to derate them. In other words, you solve that problem before you get to the auction. Having said that, the auction design in the single electricity market allows 24 hours of computations before you have to stop and say what the answer is. So you can do quite a lot after the bids have come in. But the question I wanted to put, and I have two questions, but the first question is, the really interesting question which you didn't answer with your example is, what is a battery as opposed to a great big pump storage scheme worth? So the biggest battery we had at the time would flat out run for an hour. What's its derating factor? The Irish would say 25%. Because the idea is you want to be able to have something for 4 hours. And the pump storage scheme will give you 8 hours. But the battery and smaller ones may only give you half an hour. So what is half an hour of storage worth? Or more to the point, compared to a battery which runs for an hour?
Have we got that calculation, Amy? I assume it's one that's easy to do.
Yes. So that's a sort of practical question. The really hard question for you is, okay, how do you deal with a constraint like the inability to export more from Scotland to Britain than the capacity of the transmission lines? Or critically in Ireland, between the north and the south?
So it's probably this question is more important in Ireland, because the British transmission network is pretty heavily built, and if you've got enough wind available in Scotland for the constraint to be biting, you've probably got plenty of wind available in south of the border as well, and you're not short of capacity overall. The answer is we do not have an answer to that one. We are. I mean,
is that because it's a hard problem?
Well, in our defence, we are starting to put the building blocks in place, because we have a very good new PhD student, Nestor Sanchez, who's looking at the statistical modelling for multi-area questions, and we're starting off with the 2 areas of Great Britain and Ireland. Then we'll gradually make tentative steps to 3 of splitting Ireland. Again, I think this is just an example of where there are people who've done calculations for multiple areas, but there hasn't really been a complete job done on the statistical modelling. So we're putting the building blocks in place. I think, Stan, do you want to comment on how one might, under these circumstances, run an auction?
David is quite right. It's a very important problem, and it's a very difficult problem. Partly not yet addressed because of a lack of the data necessary to answer the question. In principle, one can do the modelling, but transmission constraints, whether it be within an area or interconnectors between areas, is going to be hugely important in the future. In National Grid, haven't worried too much about it, because within Great Britain, the main transmission constraint has been between Scotland on the one hand and England and Wales on the other. and that turns out to be a binding constraint to a tiny fraction of the time. That it's not, you don't have to worry too much about it. But it's a big problem in the future.
And it leads to economic problems of the sort, when you've defined a zone that needs its own capacity, do you procure separately for that zone, or do you do out of merit bidding for that zone? How do you mitigate market power if the zone is small? So there are really a huge number of very important questions that I urge you all to solve before the next capacity auction.
So there's one from Danny.
Looking toward Anthony Papavasiliou, if you don't mind. It's because I'm looking at, you highlighted storage as a potential solution to an outage, but when you're heading towards a higher probability of an outage, so to speak, and then you start to worry about what are the circumstances in which I might be concerned, then you might want to have some sort of capacity sitting behind. And is it storage? Is it frequency support? Does it have locational characteristics? You know, how much is it about speed and ramping? So all the other things which you could throw into the conversation. And I was just wondering what's the link between the two talks?
Yeah, I mean, well, in one sense, I mean, we're not pretending to be looking at that whole general picture. I mean, we're answering a particular question that people do ask, and I mean, this kind of links also to Eddie's talk, again, referring to whether we should think about joint procurements of capacity and energy, because after all, it's the same stuff that is providing both resources. So I mean that's kind of really my answer. I guess one of the thing I would add is that the practicalities of once you bring together the sort of technical issues of optimization under uncertainty together with the kind of practical issues of how to what extent governments and decision makers are willing to quantify uncertainty in planning background when any such quantification is open to challenge because reasonable people can differ on this. Those complications are challenging enough when you're simply looking at procuring capacity, and I think all those complications would probably become greater still if you're looking at say 4-year ahead joint procurement. Janusz.
Chris, you went quickly through numbers, and I didn't notice.
Yeah.
So what are the hard numbers coming out of that for the derating value of storage, interconnectors, variable generation? Because David said 25%, right, for Ireland.
Yes.
So what's the results? Probably depends.
I mean, I should be well. I mean, one kind of big disclaimer I put on this is that I mean, what we were seeking to do here is develop a relevant methodology. We actually this is actually a very important point because I mean, throughout all the work we've done, we've been very careful not to do anything which looks as if we're doing a kind of shadow risk study, shadowing the one that we've been helping National Grid with. And there is a very real point there. That, I mean, our expertise is in the risk calculation methodology. We don't claim particular expertise in development of scenarios. But in practice, I mean, having said that, in practice, we can and possibly should have a look at these matters and get those numbers out, because they're probably they're probably not going to vary hugely between different scenarios with similar amount of storage.
But what's the range, more or less? I mean, you're trying to escape the answer, so I know it depends on the scenario.
Yeah.
But is it 50%? Is it 10%? You know, what's the range?
Yeah, Amy, do you have any comment on that, or should we take this offline?
I have the numbers on my computer. I don't know what they are off from memory. Just to answer your question, I guess you can find that it should be available in public in the capacity market report. So you've got a range basically for the duration factors. It depends on the duration of the storage. So I guess you should be able to find it.
So is it based on your analysis or some different analysis, those numbers?
I'm just talking about the National Grid report.
Yeah.
They're of the order of 50 to 75%.
Sorry?
Of the order of 50 to 75%, but it will depend on
For storage,
it
right?
depends on what the background is, and it's very variable. It varies a lot. So if you've got hardly any stores, it's big, and if you've got a lot of stores, it's small.
Right. Any further questions? I think we've got time for one more before coffee.
So, the capacity auctions are the main motivation, risk aversion, or is there other type of market distortions that would like to work around by having these capacity auctions in the UK?
I think that might be a question for David rather than me.
The incredible difficulty of predicting what politicians want even next week, let alone in 20 years' time.
That's enough even.
Yeah. Yeah. Go ahead, Eddie. Did you have?
So, Chris, you draw our attention to this question about where you need to have a scenario in place. Clearly, a lot of times one gets around that by kind of swapping time for scenarios, in the sense that we've got two equally likely scenarios, and we kind of think of ourselves as having 1 year of one and 1 year of the other, and lumping them together. Have you got any comment on that kind of analysis?
Yeah, I mean, in this picture, we, you're sort of procuring against single background. I mean, one thing one could think of if you're working in, if you had some risk target in a Bayesian decision picture, you then would have a basis to. On which to do, I think, a fairly similar thing, looking at looking across multiple scenarios. I mean, one interesting feature of the headline risk standard in the capacity market is that we have a standard of 3 hours per year loss of load expectation as the official standard, but there isn't a statement of what state of knowledge this is conditional on. So is this conditional on state of knowledge 4 years ahead? Is it conditional on state of knowledge on the Saturday of the clock's back weekend without where you know what is what exists on the system, but you don't have knowledge of beyond general statistics of what the weather will be in the coming winter, and that's something that I'm rather hoping in the present 5-year review will be clarified, because it is kind of important if you're going to have a risk standard. Sam, do you have any comments on that one?
No.
Yeah. Okay, so I think given that we've eaten slightly into the coffee break, we should. I don't know whether I'm also chairing. I should say that thank the speaker again.